All right. Electrolysis of aqueous solutions. This is an example with which we are going to start with. First, I'll go over this example so that you can always refer to the book whenever you want. But as soon as we are done with some of it, I'll come to the straightforward tips. The tips, 3 to 4 tips that you can easily memorize and can solve every question correctly. Right? So aqueous solution products are not as same as molten salts. This is because not just the salt, the water also gets involved in the electrolysis. Let's take an example from this diagram. As we've connected the battery, and there is a positive and negative end, and of course we have the inert carbon electrodes made out of graphite. We have the concentrated sodium chloride solution over here. We have taken inverted test tubes or boiling tubes, which we have collected. As we already knew in this specific system that it's going to produce a gas, that's why we made this kind of arrangement. If it wasn't supposed to produce a gas, we may not need the inverted test tubes. Then we have a glass tube in which we have the solution we are about to electrolyze, concentrated sodium chloride solution. Remember, in case of aqueous, most of the time you would be given this specific piece of information whether the solution is concentrated or not. And it may bring a difference in your results or your products. First of all, we set the apparatus as shown, glass tube, rubber bungs, electrodes together. We call all of it as an electrolytic cell. We pour concentrated sodium chloride solution in the glass tube, place the test tube containing sodium chloride solution over each electrode, and the test tubes must not be completely covered. The electrodes or ions will be unable to flow, and there will be no current. So there should be some space in between over here, as you can see. All right. So connect the battery or the power pack to the electrodes. The experiment should be done in a fume cupboard because it is going to produce pure chlorine gas, which is pretty poisonous. If you don't have the fume hood or the fume cupboard, we can use a very ventilated room for this purpose. Remember, all the halogens are extremely poisonous. So if any halogen is supposed to be produced with the help of electrolysis, this precaution is a must. And this precaution has been a part of past papers, so you can memorize it and you can write the same one in exams after. In this experiment, we'll see bubbles of gases at both electrodes. When the gases are tested, we see that hydrogen forms at the cathode, the negative electrode, and chlorine forms at the anode, which is the positive electrode. Now, we would expect to get the same volume of hydrogen as chlorine. However, in reality, we appear to obtain less chlorine than expected because chlorine is more soluble in water. So if any gas is soluble in water, we'll always get less amount of it at the specific electrode. So these are the products. How come we are able to get these products? In order to understand that, we need to understand something about water first. When we talk about water, water in its pure form is almost an insulator. However, water is a weak electrolyte, and its conductance capability increases as soon as we dissolve something into it. Its conductance capability is increased if we dissolve acids into it, because acids can easily ionize, or if we dissolve alkalis into it, they can also easily ionize. And lastly, if we dissolve a salt in it, salts are usually ionic in structure, so they dissolve in water and produce ions, which are then capable of moving and hence carrying the current, which makes water a better electrolyte than it is in pure form. So what happens? The water starts to ionize too. When water ionizes, it gives us the H positive ions and the OH negative ions, hydrogen ions and hydroxide ions. So whenever you have water present, you will have to consider these ions as well as what you have dissolved in the system. By this line, what we mean is when we write this, sodium chloride aqueous, and by the way, we took concentrated form of it, then remember, this sodium chloride would be divided into a positive ion, sodium ion, a negative ion, chloride ion. But this aqueous system, water, is also divided into positive ions, hydrogen ion, and negative ion, hydroxide ion. So instead of having two ions, which we did back in the molten systems, this one is different. We have four different ions, two cations and two anions. And whenever there are two cations or two anions, a competition starts in the whole electrolytic cell. This competition, I'm using the word competition to make sure that you understand what I'm about to explain, but you don't need to use the word competition in exams. This is just for your clarification or better imagination of what is about to happen. Now, we'll discuss both the electrodes separately. So let's first discuss the competition at cathode. We'll discuss the competition at anode separately. Starting off with cathode, we have two ions at cathode, Na positive aqueous and H positive aqueous, as I've just explained. Now, both of these ions will get attracted to the negative electrode, which is cathode. However, sodium is a very reactive metal. This means it is difficult to add an electron to a sodium ion and convert it back to a sodium atom. Hydrogen, on the other hand, is less reactive as compared to sodium. So it's pretty easy in comparison to add an electron to hydrogen ion and form an atom. So hydrogen can be converted. So this would make hydrogen go to the cathode. Sodium is so much reactive that it likes to stay in the system, and by system, I mean the electrolyte solution. So sodium being more reactive would stay as a part of the electrolyte, and hydrogen being less reactive will move to the respective electrode, in this case, cathode. This is the rule you need to remember.
I don't understand. Active one would stay.
I didn't get it. Can you come again?
Why would the more reactive element want to stay in the electrolyte?
The more reactive stays in the electrolyte because it is reactive. And when I use the word reactive, it means something that reacts quickly. Now, if they go to the cathode, they'll have to travel a lot before they can reach the cathode and go with the reduction reaction. Instead, in the electrolyte, they can keep reacting with the same system. I mean, either this negative ion or this negative ion. So it's easier for sodium to either react with this one, form the same reactant that we started off with, or react with this one, instead of moving all the way to the cathode and then getting reduced over there. So sodium being reactive does not prefer a lot of, you can say, commuting before it reacts. Being reactive means it would react as it is, wherever it is. Hydrogen, on the other hand, is less reactive. So even if it has to travel to get a chance to get reacted by electrons and being converted into hydrogen gas, it would take a chance. Because sodium will cover the entire electrolytic space in order to react with any negative ion it can come in front of. Do you get the point?
Yeah.
So sodium is not just reactive. If you're going to imagine it, you can imagine it as a hasty substance, a substance that is in pretty much of a haste to get reacted with anything, hence the word reactive. The more reactive something is, the greater tendency it has to form an ion, which means that more reactive something is, the more difficult it is to turn back into an atom. So for positive ions, such as sodium, they like to stay in the same form. Hydrogen is less reactive, so hydrogen is capable of this compromise of being converted back to its atomic form. Sodium does not. Being more reactive, it likes to stay in its positive ionic form. That's what this reactivity means. So either you go by the perspective it likes to react with these two negative ions, or you go by this perspective that means it's difficult to convert it into its original atomic form. Both the perspectives are correct, and both the perspectives explain the term reactive in this case. Okay, so what happens is that sodium is going to stay over there and hydrogen is going to react. Each time hydrogen ions come from water molecules splitting up, our water molecule ionizes. It also produces hydroxide ions. So there is going to be a buildup of those ions in the system. So water would break down, produce hydrogen ions, which are converted into hydrogen gas, and we are left with a buildup of hydroxide ions in the solution. And that is around the cathode. All right, keep this in mind because we're going to pretty soon use it up. There is an alternative way of looking at the reaction at cathode. At cathode, water can get reduced, which means the entire water molecule can gain electron just like this, is converted into hydrogen gas and hydroxide ions. So water can get reduced. This is an alternative way to understand the same thing. So whichever way you pick, it's all about the concept. I haven't given the tips yet. First, we need to understand the concept so that if there is any theoretical conceptual question, you can answer it. Even if you don't understand the concepts, the tips can get you to the right products easily, as well as the correct equations. However, if there is a 2 to 4 mark theoretical concept question, which sometimes there is, not all of the times, sometimes, then you need to answer them in the concept of theory. All right. So when this keeps happening, the ionization of water becomes a one-way process, just as written over here, which means water keeps on breaking down into hydrogen ions and hydroxide ions, hydrogen ions which are later converted into hydrogen gas, hydroxide ions which we are going to use on the next page. Okay. The concept might seem a little difficult enough, but don't worry, when I'm going to come to the tips, it would become easier for you to understand. Let's talk about what's going to happen at the anode. Cl negative ions, as I've explained earlier, and OH negative ions are both attracted by the positive electrode, which is anode. Now, it is slightly easier to remove electrons from oxidize the hydroxide ion than from chloride ion, but there isn't much difference. Now, in these two cases of these two, there isn't much difference. We can easily oxidize this one or this one. Now, it really depends upon the concentration. So, this reaction is possible as well as this one. All right. So you're supposed to memorize this reaction about hydroxide ions. And it's already written over here that it is unlikely that you will be asked about how this reaction occurs in IGCSE. So you just need to memorize the reaction. So this reaction is possible. This reaction is also possible as they are equally attracted and equally easy to remove electrons from these ions. So both of the reactions may happen. What does it depend upon? Let me explain. It depends upon concentration. If this is more concentrated, then means there are more Cl negative ions. So of course, it is going to convert it into this product. If the system is dilute, that means it has more OH negative ions. And in this case, OH negative would be converted into our required product. Remember, OH negative has three products: water, oxygen, electrons. So it is going to form oxygen as our product. As water is already a part of the system, we do not consider it as an active product. The only product we consider active is oxygen. However, you need to write the whole reaction whenever it's asked in exams. All right. So what happens at anode in this specific case, as this is a concentrated case, it produces chlorine at anode. So take a look at this. From NaCl, we have Na positive and Cl negative. This went to anode. From H2O, we have H positive and OH negative. This went to cathode. So we are left with Na positive and OH negative in the system. which react with one another to form NaOH sodium hydroxide solution. There were only two products back in the molten systems, but in aqueous systems, there are three products, one at cathode, one at anode, and one that's left behind in the system. Are we good?
Yeah.
Okay. I'm going to send you something which is going to help you with the tips I'm about to explain to you. Just give me a quick second. So rules of solutions. Rules of solutions are pretty simple. Let's first talk about the cations. In case of cations, we use the reactivity series. Are you familiar with the reactivity series?
Yeah.
Okay. Instead, I should take it from the book. Wait, let me change it and use your book so whenever you need to refer to it, you can easily do. Okay, there you see the reactivity series in front of you. This is page number, can't see the page number really, page 109, all right? So on this page, you will find the reactivity series. Now let me explain how I'm going to talk about the rules for cations. In case of cations, I hope you understand whichever salt I use, it would give us a positive ion and a negative ion. But every time a salt is dissolved into water, water is also always going to give us a hydrogen positive ion and a hydroxyl negative ion. Talking about cations, this is the positive ion that is a must in every aqueous system. So whatever this positive ion is, it has to compete with hydrogen to either stay in the system or get retracted by the cathode in order to be removed by cathode, of course, by the reduction reaction. So there lies the hydrogen. Every element there is in this list, we need to compare it with hydrogen. And you would see that most of them are more reactive than hydrogen, an entire list. However, only a small part of the list is less reactive than hydrogen. So as I've explained, if it's more reactive, then the chances are it would stay in the system, right? And if it's less reactive, the chances are it would go to cathode, all right? And if we look at this list, which elements are capable of going to the cathode in comparison to hydrogen? Only these three. Do you get the point?
Yeah.
So as only copper, silver, and gold are less reactive than hydrogen, so they are the only metals in the entire reactivity series which can go to the cathode and get deposited over there. Otherwise, with every salt of potassium, sodium, lithium, calcium, magnesium, aluminum, zinc, or iron, whenever they are dissolved into water, always hydrogen would go to the cathode and will form hydrogen gas. The reaction is pretty simple. 2H positive, after the gain of 2 electrons, are converted into hydrogen gas, like this. Only in the case of copper, silver, or gold will they go to cathode. Otherwise, every time there would be formation of hydrogen gas at cathode. Easy enough?
Yeah.
Good. This concludes the cation rules for us. In aqueous systems, the cations are always going to work according to the reactivity series, which is actually pretty easy. And take a look over here. We had a comparison of sodium ions and hydrogen ions. According to reactivity series, this is less reactive, so this goes to cathode, and sodium is more reactive, so this stays in the system. So the same thing happened in the process we just studied. Okay.
Yeah, okay.
Then let's talk about anions now. In case of anions, I've already explained a situation. Let's consider that situation again. It was the situation in which we talked about hydroxide ions and chloride ions. Let me bring you to that page. And we said they're equally easy to be oxidized into the relative products, either this one or this one. As I've explained, if we talk about anode, water always gives us the negative ion, which is OH negative. The salt can also give us a negative ion. We don't know what that can be. Either that can be chloride or bromide or iodide. All right. So all of these in comparison with OH, this is concentration dependent. What does that mean? If the word concentrated is written with the salt, the chloride are going to be converted into chlorine as per this reaction. A very similar reaction can convert bromide ions into bromine or iodide ions into iodine. If the salt is concentrated. If the salt is dilute, that means it has a higher concentration of OH negative ions. So, of course, this is going to be converted into oxygen gas with this reaction. So it's pretty easy. If the salt consists of a halogen and it's in concentrated solution, a halogen would be given out at anode. All right. But if the salt is made up of a halogen and the salt is taken as a dilute solution, it would give us oxygen gas at anode by the similar reaction written over here. Are we good?
I don't really understand what's happening at the anode.
Okay, at anode, we have two different ions, right?
Yeah.
At cathode, we discussed that we can always take help from the reactivity series.
Yeah, depends which one is less reactive.
Yeah, good. So there is no reactivity series for negative ions. How are we going to compare them then? Actually, what I'm trying to explain is that they are concentration dependent.
Okay.
So if the word concentrated is used with the salt and it consists of a halogen, a halide ion, it would be produced at anode. But we can take a dilute solution, and in that case, as there are more OH negative ions, oxygen would be produced by this reaction. Let me explain that with the help of an example. If we are going to perform electrolysis on sodium chloride concentrated aqueous solution, anode will show us signs
Will it
of
always
chlorine
be
gas.
concentrated?
No, it
Will
can
it always
be
be a
dilute.
concentrated?
No.
Oh, okay.
So the second type of example are the dilute examples. What if we take a dilute solution? A little amount of salt and a huge amount of water would easily form a dilute solution. In that case, anode would give us oxygen gas because of this reaction.
Okay.
All right. Why do we have oxygen in this case? Because there are more numbers of hydroxide ions, because it's dilute. Dilute means less concentration of salt, more concentration of water. So water gets electrolyzed. I mean the hydroxide ion. Of course, we're talking about the negative ions only. All right.
Okay.
And if there is concentrated means more salt than water. So of course, the salt gets electrolyzed. The negative part of the salt is chloride ions, which are then converted into chlorine gas.
Okay.
So the anode product changes as the concentration changes. There is no change in the cathode product due to concentration because they're not concentration dependent. They are based on reactivity. However, in case of anode, they are based upon concentration. When this is compared with these three ions. Are we good?
Yeah, that makes more sense now.
So whenever there is a dilute salt, you can easily form oxygen with this equation. So memorize this equation because every time there is a dilute salt, you're supposed to form oxygen. Only in the case if there is a concentrated salt, these halides will give us respective halogens.
So if it's diluted, it will always produce oxygen at the anode.
Right, it does.
Then why do I need to remember the formula?
Which formula?
The four.
Yeah, this entire equation has to be remembered because if they ask you to write the equation, the anode half reaction, you're supposed to copy this one.
Oh, okay.
Because we're supposed to write equations, just like we have written this one for anode for chloride ions. In case of concentrated, we might need this one in case of dilute.
Yeah, okay.
Right? But there is still one small issue. At anode, we might not be using this, or this ion. We might not be using any halide ion at all. What do we do then? What if we use polyatomic ions such as nitrate or sulfate or phosphate or a carbonate probably or a hydrogen carbonate? What if we use polyatomic negative ions? What then? It's pretty easy. If any polyatomic ion is used, any in the word, more likely oxygen is supposed to form in the same way. And the polyatomic ion will stay as a part of the system. So that's pretty easy. So if we are going to compare this versus any polyatomic ion such as this would form oxygen at anode. Easy. Okay. Let's practice a few questions.
Okay, then
so
what
this
would
comes
the half equation for that be?
This one, the one that is
For
written
the
in purple.
polyatomic.
Yeah, this one. Why? Because
It's
the
the
half
same.
Yeah, it's the same. That's the best part.
Okay.
For anode, most of the time the result is oxygen. The only time we have a different result is that if we have a concentrated halide salt present.
Okay.
Okay, now let me cut it down to you into two simple small parts. For cations or for cathode, the only time we were using an equation different to hydrogen's equation was when there was copper, silver, or gold in the salt. Only then you're supposed to have a different equation than hydrogen's equation in case of cathode. In case of anode, the only time you're supposed to come up with a different equation is when you have a concentrated halide-based salt, chloride, bromide, iodine. Only then a halogen is produced. Otherwise, every time, be it a dilute salt or a salt with any of these polyatomic ions, it would always be this equation of oxygen. So there are two major equations which cover most of the part of answers in aqueous systems. But actually this comes as a little confusing to students, so they don't see the whole picture. The whole picture is this, that they are pretty easy. Most of the time you're ending up with hydrogen at the cathode and oxygen at the anode. There are hardly 3 to 4 different cases when you have a product other than hydrogen at cathode or a product other than oxygen at anode. Hardly 3 to 4 cases. And if you can remember those 3 to 4 cases, electrolysis is a piece of cake, actually. Right?
Yeah.
So
Okay.
when do we have an equation other than hydrogen as at cathode? If there is copper,
It's less
sulfur,
reactive than hydrogen.
right, it's less reactive than hydrogen. Anything less reactive than hydrogen, if that's present as a part of salt dissolved in water, we have an equation different than that of hydrogens at cathode. And when do we have an equation different than oxygen's equation at anode? When we have these three ions in concentrated form. These three ions and that also in concentrated form. Even if these three ions are present in dilute form, it forms oxygen. So most of the time it is oxygen gas at anode. Pretty easy. Okay, so let me show you an entire table to give you a very good idea of how this happens in case of this table writes the same thing. Okay, take a look. For concentrated NaCl aqueous, we have hydrogen and chlorine produced at cathode and anode respectively. So we are only left with sodium hydroxide as a change to electrolyte. Okay. Do we get it? This is hydrogen because hydrogen is less reactive than sodium. And this is chlorine because it's a concentrated salt.
Yeah, I understand.
Now, in case of dilute NaCl, it's hydrogen and oxygen. It's pretty easy. Hydrogen is less reactive than sodium and oxygen because it's a dilute salt. So for potassium iodide concentrated, again, hydrogen because hydrogen is less reactive than potassium, and iodine, why? Because it's a concentrated salt. All right?
Yeah.
And next up is dilute Ki. It produces hydrogen and oxygen. Why? Hydrogen is less reactive than potassium, and oxygen because it's a dilute system. All right?
Yeah.
Okay. I am getting a very important call over here. So can you give me a couple of minutes? Electrolysis, copper sulfate using inert electrodes. Now this is the one we just looked at in the previous portion. I mean, the Word document we were just looking at.
Yeah.
So this is also an example in which you see copper ions. So what happens is that this time you won't be able to write the equation for the formation of hydrogen because copper is less reactive than hydrogen. So instead, copper goes to the cathode and forms solid copper, which is a pink brown element that is coated at the cathode. As you can see over here in the color, this is copper coated on the graphite electrode. Sulfate ions, hydroxide ions from the water will be attracted to the anode. Sulfate ions aren't easy to oxidize. The simplest lines IGCSE use at this level. So simply OH negative ions are going to produce oxygen as a product. Although you're supposed to memorize the whole equation, but when they ask the name of the product, oxygen is good enough because water is already a part of the system. Right?
Yeah.
This is an alternative equation. This is only given in this book. Alternative equation to this one. Here they use less number of water molecules. They use water molecules to be converted into oxygen and hydrogen ions. Okay.
Okay.
We actually use this equation because this equation explains easily why the system is a little bit acidic at this point. As you can see in this specific equation, you would see that the water is being converted into oxygen and H positive ions, which are actually acidic in nature. That's why wherever this is happening, the solution would become slightly acidic. On the other hand, the positive electrode, you would see colorless bubbles of oxygen. Which brings us to the last part of the electrolysis, that visible observations are also important. Gases are seen in the form of bubbles. Colorless bubbles depict gases such as oxygen, nitrogen, maybe hydrogen, although nitrogen never forms in the system, so mostly oxygen and hydrogen. However, they can be colored gases as well. For example, if Cl2 is produced, it has a pale green color. If Br2 is produced as a gas, it has red vapors or red bubbles.
We need to memorize the colors also.
Right. You need to memorize any visible observation. One of the visible observations is copper being deposited, and as quoted over here, it's a pink brown metal or a red brown metal coated on the top of cathode. Right? Not just that, this system is actually of blue color because of copper sulfate. CuSO4 is blue in color in aqueous solutions, right? So if the electrolysis is continued for a long period of time, the copper 2 ions will actually be used up. I mean, they're deposited at the cathode in the pink brown form, so the color of the solution will fade from blue to colorless.
Okay.
So it fades to light blue and then finally to colorless after some time. So from copper sulfate, copper ions went to the cathode. They were converted into copper at cathode, and they were converted as oxygen on anode. So what are we left with? This one is going to be good. Now, H positive and SO4 negative will react with one another. And when they react with one another, let's react them separately as they have different states. So this would go over here and this would go over here. It would form H2SO4. So yeah, it forms H2SO4. In order to balance the whole equation, you need to put a 2 over here. So that's what happens to the system. The system, which previously consisted of a copper sulfate solution, is gradually converted into a colorless solution of sulfuric acid, which is mentioned over here and here. Your book does not mention the equations for the leftover substances or ions, but you should be able to do that in exams.
Yeah.
Right. So whichever, it's a pretty good idea to write all 4 ions at the start. Take one of them at cathode and one of them at anode. You're left with 2 of the ions. React those 2 of the ions, and that's what you're left in the system with. Started off with copper sulfate aqueous and left off with sulfuric acid in the system. So that's why electrolysis of aqueous solutions is very different in terms of its products than the molten systems. Okay. Now, one more important point that has been used in past papers as a question. The reason that we keep stressing the use of inert electrodes is what the electrode is made of can sometimes affect the products you get. If you use copper electrodes, oxygen gas is not produced at anode, but rather the anode gets smaller. This is known as electroplating. All right. So it's important that you take inert electrodes and you don't take the electrodes of the same material of the ions which we are getting as cations. I mean, the cations were made up of copper, so do not use copper electrodes over here. Okay. because they then interfere in the entire system and a different set of results are obtained. Let's talk about the electrolysis of dilute sulfuric acid using inert electrodes. So we get H positive ions at cathode, which are going to give us hydrogen gas at cathode. This would be produced at cathode, which you can see over here. And this would be produced at anode, as sulfate ions cannot form at anode, so you can see it over here. So we took a dilute sulfuric acid collection and we took platinum electrodes, we produced hydrogen and we produced oxygen. Twice as much hydrogen is produced as oxygen, because if you look at the half equations above, for every 4 electrons that flow around the circuit, we get 1 molecule of oxygen but 2 molecules of hydrogen. That's because the formula of water also consists of 1 atom of oxygen and 2 atoms of hydrogen. So if you're going to break down water molecules in a proper go, that means it would produce 2 molecules of hydrogen and 1 molecule of oxygen upon breakdown, which can be written or explained like this. This is the balanced chemical equation. Now, you must be thinking that I started off with the heading of dilute sulfuric acid electrolysis, and instead the equation is all about water. So remember, for dilute sulfuric acid, nothing happens to the sulfuric acid and water is electrolyzed because hydrogen is forming at cathode and oxygen is forming at anode, which actually happens with the breakdown of water. The same thing is explained in this paragraph, how we get 2 molecules of hydrogen and 1 molecule of oxygen from this breakdown of water. And a few extra things are explained over here too. So actually, when we do this experiment, the amount of hydrogen we obtain is twice as much as the oxygen. This is because oxygen is more soluble in water than hydrogen. So this is sometimes what we do to stop this happening is to carry out the electrolysis experiment for a few minutes first in order to saturate the water with oxygen and then start to collect the gases, which gives much better results. Okay, so what we explained to you in theory or what explains what happens actually may be different. Are we good?
Yeah, I think so.
Okay. Actually, sometimes your book caters even the smallest of issues practically or theoretically. So your book covers this up with the entire 3 points that I've stated. So if the metal is high in reactivity series, hydrogen always gets produced at cathode. Only in the case if metal is low hydrogen in the reactivity series, you get that metal at the cathode. If the solutions of halides, chloride, bromides, or iodides, you would obtain the halogen at the anode. With other common negative ions, sulfate, nitrate, hydroxide, you'll always obtain oxygen at the anode. So these are the 3 tips you need to keep in mind for electrolysis. If you remember these 3 tips, you will always be able to get the correct products. And there is also an electrolysis table given in your book. You will always be able to come up with the correct product. What would happen with non-electrolytes? For electrolysis to work, there must be some ions and there must be conductivity. Lastly, we have quantitative electrolysis. Quantitative means something related to numbers. It means we can always work out the amount of product produced for the specific amount of reactant used in electrolysis experiment. we can always investigate the amount of product. For example, investigating the effect of changing of current on the amount of hydrogen produced at cathode in the electrolysis of sodium chloride solution. To do this, we use similar apparatus as we have discussed previously, but we will also have to put a variable resistor and an ammeter into the circuit, and we can vary the current and measure the current easily. Variable resistors will help us to vary the current, and ammeter would help us to measure that current. We would also have to use a gas burette or a measuring cylinder to measure the volume of gas produced. We can use a gas burette or we may use a measuring cylinder. As test tubes are not graduated, so a gas burette or measuring cylinder would easily help us to calculate the amount of gas collected. Set up the apparatus as shown over here. Pour 50 cubic centimeter of concentrated sodium chloride solution in the glass tube. Place the gas burette filled with sodium chloride solution over the cathode as well as the anode. Turn on the power pack, connect to the battery, and set the current to 0.2 amperes using the variable resistor. Take the initial reading on the gas burette. We have to start the current flowing so that we can see what the current is. Therefore, we only take a reading on the gas burette after we have turned on the power. Start the timer. Stop the timer after 5 minutes. Note the final reading is on gas burette. Repeat it for different volumes with the step-ups of 0.2 ampere every time. So that it's 0.2 for the first one, 0.4, 0.6, 0.8, and 1.0 for the fifth experiment. Repeat the experiment for reliable results. And if your answers match closely, you're probably doing it correctly. All right? Like this one. In this one, you would easily understand that your experiment in all the times are correct except for the third one, 0.60 amperes. That either was not done correctly or was not measured correctly, which also the graph tells you. So we can easily form a graph between current and volume of hydrogen to get an idea for how much specific amount of current, what volume of hydrogen can be produced. Also, we get an idea that if the current increases in amperes, the volume of hydrogen also increases, which means it increases the rate of reaction in an electrolysis experiment. All right, which actually finishes the chapter for you.